want to first outline the problem or the issue that we're trying to talk about. It's basically Ampere's law, the way we took it before in a previous chapter. If you take any closed contour, I call it here a closed loop, but it's a closed contour, any closed contour. Like for instance, imagine a rubber band. That's a closed contour, and you can make it of any shape you want. It doesn't have to be even in the same plane. It could be in any plane. It could be not in one plane. And imagine you have some currents that are going through the surface bounded by this contour. So you have here current I2 going this way, current I1 going this way. Current I3 is not going through the surface that encloses the loop. So this was Ampere's law. We said that the integration of B dot ds, if you integrate the magnetic field dotted into the elements of length ds, these green vectors are the elements of length ds, around the closed contour, the right-hand side, it says it should be mu naught, which is a constant, times the current enclosed. Current enclosed means you only take the current or the currents that are going through the surface that's bounded by this contour. So this was Ampere's law. If you don't remember it exactly, go back to what we did before because it was done in detail. We said also before that we can change the right-hand side. Instead of saying mu naught times I, we know that the current in general can be written as integration of J dot dA, current density dotted into area. But we said before also in detail that we need to make a very specific choice of the relationship between the ds vectors and the dA vectors. If the ds vectors are going around this way, then you use the right-hand rule as drawn in the picture here. You put your fingers in the direction of the ds vectors, then the thumb will point in the dA vector direction. Because for this surface, for instance, there are two different directions for the area. You could make it go up or down because it's an open surface. No, we have to make it very specific. And if ds and dA are not related in this way, then this equation will not be correct. So this is a criteria for making this equation correct. You have to have this relationship between ds and dA. Again, this was discussed in detail before, so if you don't remember, go back and see what we did before. So that's, so far it's fine. This is what we've done before. Comes the issue. If the closed contour, this closed contour, is not in a plane, but it's in general in any shape in 3 dimensions. For instance, you get a elastic band in a closed loop elastic band and reshape it in any direction you want, any shape, so it's not in one plane. Then the question becomes, which surface do we mean when we want to calculate this integral? To calculate this integral, you need to choose a surface. So which surface should we take? It might be, you might think it's easy to find the surface if the contour is in one plane, then you can just take the surface that's in the same plane as the contour. But what if the contour is in 3 dimensions? It's not in the same plane, there's no unique surface to calculate this integration through. What if I, for instance, take this curved surface? This surface can be imagined, if you know, like the game that they have where they have the wire and they put the wire into soap and then they blow the soap bubble and it becomes elongated like this, and if you blow more it can actually make a bubble and go off. This is exactly the same kind of geometry. You have a closed contour and you want to make a surface, any surface that's bounded by this closed contour. So there are an infinite number of surfaces that are bounded by this contour. This one that I tried to draw in a kind of 3-dimensional way is one of them. So if you take this surface instead of the other one, the flat one that we took before, and you calculate integration of J dot dA, will you get the same answer? This is very important because if it doesn't give you the same answer and there's no unique surface, then this equation really has a problem. There's a problem here. So if this is basically where what the problem comes from. So if you want to write a law like this, such that the right-hand side will work for any surface bounded by the closed contour, if you want to write the law in this form, we need to see if this integral is the same for all the surfaces. If it's not the same for all the surfaces, then there's going to be a problem, because if you calculate this right-hand side for say the flat surface, and you get a number, and you calculate this surface integral for the curved surface, you get a different number. That means you're getting a different value for the magnetic field. The magnetic field is a unique value. If you integrate B dot ds around this loop, you should get a unique value. So you can't have a right-hand side that depends on the kind of surface you're choosing. So this is where the gist of the problem is, and if you don't understand this part, try to understand it better, and if you have any comments, write down some comments, and I can explain things better. But this is important before we move on.